I'm Tim Ventura, and in this presentation, Dr. Kent Peacock discusses the No-Communication Theorem, also called the No-Signaling Principle, and explores fundamental logical flaws in this negative proof that may facilitate the future development of superluminal quantum communication. Dr. Peacock is a professor of philosophy at the University of Lethbridge and is a philosopher of science focused on physics and ecology. He also has strong interests in the metaphysics of time, logic, environmental ethics, the nature of ingenuity and creativity, and the complex challenges flowing out of humanity's current ecological crisis.
So begging the signaling question, based on work I did a long time ago as a graduate student, published on this a few times. I've been doing other things in my life as well, but I keep coming back to this issue, and I'm grateful for the opportunity to talk about it. Okay, so the conventional wisdom says it's impossible to use quantum entanglement to signal controllably faster than the vacuum speed of light. And I belong to a small group of people who have independently questioned the conventional wisdom. And so I'm going to try and give you a sense of why, what we're on about today. And just to give credit where credit is due, here's a few names. So P.J. Bussey in 1987 has a paper where he, and I'll quote him in a second, J.B. Kennedy Jr., very good detailed paper. Peter Mittelstadt, German physicist, and a few things by me, including, I think the first item is my PhD, second item is a short commentary I published in Physical Review Letters a long time ago. And then I've collected a lot of my stuff on this. And then this paper with myself and Brian Hepburn, a former student of mine. And then I have a little collection called Quantum Heresies that can be gotten through Amazon from college publications. So, so here's a comment. I'm going way back to 1987. Here's how Bussey put it. And this is essentially what we're saying here. Non-communication in EPR experiments and standard formulations of quantum theory is obtained trivially by means of ad hoc assumptions about the behavior of multi-particle amplitudes rather than as a consequence of basic physical principles. So ad hoc obviously means something that's just sort of, in computer jargon, it's a patch. Okay, we got to solve this one particular problem, so we'll make up a special rule just to solve that one problem. But we don't really have an argument in principle. So some background is needed to see where all this is coming from. So J.S. Bell said, get a good text. So the book that I've used quite a bit is this book from 1977, Cohen-Tanucci et al., Quantum Mechanics, Volume 1. And there's my battered copy of it here. And this book is very, very good on the mathematics of entangled states. So it's a good place to start. Obviously a little out of date in some respects, but very good introduction to the basics. So what are entangled versus product states? That's the first distinction we have to make. And I don't want to get too technical here. I'm just trying to give people an intuitive sense of the issue. So suppose P1, P2 are a couple of particles, electrons, protons, something. They could be almost any kind of particle you think. So each state is said to have what's called a state vector, or people call them qubits now, that lives in an associated Hilbert space, which is a complex valued vector space. And you might say, well, why? Where does that come from? And the answer is nobody really knows. This was discovered in the 1920s because it works. So in a sense, quantum mechanics was reverse engineered from the phenomena. That we found mathematical rules that are very good at predicting the phenomena, but at a certain point, you hit a wall. So why do we use Hilbert space? What are these qubits? What's the relationship between a qubit to the actual physical things? We don't know. So, but let's just move on. So what happens if you combine their state vectors? If you have two particles, if you consider the two particles as a single system, and the trick here is to sort of think holistically. We're talking about a pair of particles behaving as one. So if the particles never interact in any way, you write what's called a product state, which is just, you take the states, the two independent particles, and multiply them. And I'm not being absolutely algebraically correct here, don't worry, but this basically illustrates, gives you a sense of what's going on. So product states evolve independently. So they're sort of like successive tosses of an honest coin. They don't correlate with each other. They don't influence each other. However, if the particles have interacted in any way whatsoever, we have to write what's called the tensor product state. And what this jumble of symbols here means is you're taking what's called a linear combination of all the possible products of all of the possible substates of each particle. And they're multiplied. The CIs are just complex coefficients, which are not all going to be the same. And why do we have to do this? It's because of the fact that, I don't want to get too much into this, but it's because of the fact that these are linear objects and they obey the superposition principle. So all possible linear combinations of the vectors in the two subspaces are allowed vectors. And that's what this expresses. So this comes fundamentally from the superposition principle. Okay, so here's an important example called the singlet state. So this funny looking animal here, the 1 over root 2, you can ignore. It's just what's called a normalization factor. It's just a number. This is the important part. So these little things. This denotes the state of two possible states here. This is the state where the left particle is in spin up and the right particle is spin down. And this denotes a state where the left particle is spin down and the right particle is spin up, if that makes sense. And you have to think of not the state of the individual particles, but the state of the system as a whole. It's something that can be up, down, or down, up. Right? And anyway, there's a lot of, there's many, many other entangled states, but the singlet state is relatively simple. So people often study it in theoretical theoretical considerations. So very important fact, it's mathematically impossible to factor this state into states belonging entirely to each individual particle. And that's a pretty simple demonstration. So if you try, you end up with stuff like 1 equals 0. It's just a mathematical contradiction in terms. You can't break this up into a state of the left particle multiplied by the state of the right particle. You have these are called excuse me, these are called cross terms. You have these cross terms and they won't go away. So Schrodinger actually introduced the term entangled or entanglement, but it's the same thing as non-factorizability. It's just a more picturesque term. Okay, so now the important thing, entangled states exhibit certain correlations between the measurement results that you can get. These correlations generally take the form of sinusoidal functions, sines and cosines. So for example, the singlet, the correlation function has the form cos squared theta 1, 2, where theta 1, 2 is the relative angle between detectors. So at the two remote experimenters at the two distant testing sites have some kind of detector that we don't have to get into the details of that, but the detector it's like a thing with a magnet in it. It has you can set them they're at some relative angle, and the correlations are a function of the relative angle. So this is the germ of non-locality already right here. In some sense, each particle knows the angle that the other detector is set at. How does that happen? All right, so then we bring us to something called Bell's theorem, which Henry Stapp described as the most profound result of modern science. And I think he might be right, but there's a lot of disagreement about what Bell's theorem means. I'm going to give you in one slide the very short version of Bell's theorem. So it goes back to Einstein. And so Einstein's firm belief was that the quantum correlations were the sign of some kind of information or structure encoded in the individual particles at the source, because he thought it was absurd that there could be any sort of direct influence of one particle upon another at the time of measurement, because they could be arbitrarily far apart. It could be at opposite ends of the galaxy. So J.S. Bell called this the genetic interpretation of quantum mechanics. And the simplest way to intuitively explain it is compare it to actual genetics. So I happen to have a brother. We're not twins, but we do resemble each other. Why do we resemble each other? Well, it's not because of spooky action. It's because we share a lot of DNA, which we got from our parents. So the idea, so Einstein's idea was, I mean, they didn't know about DNA in 1935, but his idea was there's sort of a DNA, if you, something like, sometimes people call it hidden variables, but whether or not it's hidden is not actually the relevant point. The relevant point is it's localized to each particle. It's like encoding that's built into each particle, just like our genetics is built into our bodies, right? So that's the idea, the genetic interpretation of quantum mechanics. And then J.S. Bell in 1964 published an amazing paper, which should have won the Nobel Prize. So that's why it's the Nobel Prize, right? Sorry, that's my pun for the day. But anyway, Bell showed that if the genetic interpretation is correct, the quantum correlations must be restricted by certain mathematical inequalities. However, it's very easy to show that quantum entangled systems violate those inequalities all over the map. And then it took about another 15 years for people to set up experiments that tested this prediction, but everybody knew Bell was right. They didn't. So in a very short version of Bell's theorem, there is no quantum DNA. There can't be. It's mathematically ruled out. So what's actually going on? Well, again, that's a huge literature debating this point. What Bell himself said in an interview in 1988, I think, is maybe there must be something happening faster than light, although it pains me even to say that much, because it's the only option left. And so what I ask is, why the pain? Why should this have pained Bell or anybody else? Why didn't they just go, that's incredibly cool, we should investigate this? But there's been, it's sort of like, it's almost like, you know, like there's climate science denial. It's almost like non-locality denial. It's people just don't want to hear about this. Anyway, so let me go on. So you can explain this in the context of the famous Einstein-Podolsky-Rosen thought experiment, which is very complicated. I've spent a whole graduate seminar going through this thing line by line, but the basic picture is very simple. So you have a source down here which emits pairs of entangled particles. And then we have two experimenters, let's say Alice and Bob, because they're in everything. Alice and Bob are at a space-like separation from each other. So this is a space-time diagram, time in this direction, space in this direction. And Alice has her detector set at some angle, Bob has his detector set at some angle. And we imagine the source emits pair after pair of entangled particles, as many as you need, right? And Alice and Bob just write down the results they get, which will be spin up, spin down, spin up, spin down, or maybe up, up, down. And so what they will see, we know this very well, what they will see, in fact, is each person will see what looks like a completely random sequence of pluses and minuses. It'll look like the results of a toss of an honest coin. It's just a random sequence of plus and minuses. But here's the interesting thing. Those pluses and minuses turn out to be correlated by that co-squared theta 1, 2 function. So Alice could, in fact, vary her detector. She could flip the angle back and forth, or Bob could too, they both could, in such a way as to build a message into the correlations. She could encode a message in the correlations. But this is not quite the same thing as superluminal signaling, because you need both sets of experimental results to read the message. So Bob's string of results serves as the key for Alice's, and vice versa. So this idea is the basis of something called quantum cryptography, which is a very real thing. And there's no controversy that this is real. And lots of people work on this, and very significant money is being spent on quantum cryptography. So what I've said to you up at this point is completely accepted, and it's just quantum information theory 101. Okay, so, but the question now is, could Alice send a message that would show up in Bob's local statistics? So how could she do that? Well, she might think, well, okay, if I could just force my particle to say go up or whatever, some particular direction. And Alice isn't a skilled experimenter, so she knows how, she's got some magnets and stuff, and maybe she could do that. If he could force her particle to go up in a particular direction, could that encode a message in Bob's local statistics. But if she could do this while maintaining the correlations, she could do it. So that's the catch. Can the local observer make experimental choices at their end of the apparatus in a way that sends a message that does not destroy the correlations? But what actually happens in any real experiment that we know about is that, yeah, sure, Alice can start to steer her little particles one way or the other, but it washes out the correlations. It just turns the correlations into random hash at that point. You wash out the correlations, and it behaves like a product state. So product states can, of course, be correlated, but the signal has to be built into them at the source, just like genetics built into. I mean, again, you and I, our genetics are built into us at the source from our parents, right? So as far as I know, and I sit to be corrected here, no one has, as a matter of practical fact, been able to do what I'm describing here, even though it actually sounds like it might just be an engineering problem, right? But nevertheless, what people say in the literature, and there's many, many, many papers basically arguing this in different ways, is that Alice shouldn't even bother trying, because it's impossible in principle for her to do anything that could control her local results and maintain the correlations at the same time. Right. So, and the question is in principle. So that's the claim. So it's, I mean, there's obviously an important distinction. In 1890, people didn't know how to do heavier than air flight. And there were actually a couple of scientists who thought they'd produced in principle proofs that it was impossible. And they're just historical curiosities now. I mean, because a few years later, the Wright brothers showed that, no, it's just a matter of engineering. You had to have a powerful enough engine and know something about aerodynamics. And yeah, you can have heavier than air flight. So that's the question about signaling. Is it just a question of some kind of engineering, or is it a matter of principle that you can't do it? So anyway, I've read a bunch of the no signaling papers. There's dozens of them. I haven't read all of them. And they work in many, they often use very different sort of algebra. Some of them are very mathematically sophisticated. Basically, they can be classified in two groups, some within non-relativistic quantum mechanics, some within quantum field theory. We don't have time to get into all particularly the field theory proofs, but the gist of it, one way or the other, regardless of what algebra they use, they all assume that whatever Alice can do to her particle, it has no dynamic interaction with Bob's particle or measuring system. They assume that anything Alice does is entirely local to her particle or her laboratory. Now, given that assumption, surprise, surprise, Alice can't impose a signal on Bob's statistics any more than you or I could talk if we didn't have telephone line or Zoom or fiber optics cable or sound waves or some means. There has to be some physical interaction to communicate, right? So you just assume there's no physical interaction, and lo and behold, just do a bit of algebra and you get Alice can't affect Bob's statistics. So that's what I and these other authors have all been questioning, because basically what we say is, wait a minute, you're assuming something that actually wasn't that what you were supposed to prove? I thought we were supposed to see whether anything Alice does could affect Bob, either controllably or otherwise. And you just flat out assume that it's impossible from the outset, which is kind of giving the whole game away, right? Okay, now I'll just briefly dip in a slightly more technical level, because this is something that I've worked on a little bit. One version or several papers in the no signaling literature use the assumption that the Hamiltonian is additive or local. And I've cited a paper by Abner Shimoni from 1983, that's a widely cited paper. So the Hamiltonian is a quantum operator that gives you the possible energy states of the system. And what Shimoni and many other people have done, is you simply assume that the total Hamiltonian of the multi-particle system is just the sum of Hamiltonians you can assign locally to each individual particle. So again, it's another way of expressing the idea that these two particles are dynamically independent. One has its energy states, the other have its energy states. They have nothing to do with each other, right? And this is used in many no-signaling proofs. It's also very important in something called local quantum field theory. And if this was wrong, local quantum field theory would have to be fixed. And that's probably a bit above my pay grade, but it's a problem. Anyway, let's just leave that aside for now. The crucial point about this locality is it's just an assumption. Shimoni just assumes it. Other people just assume it. And why do they do that? It's because they strongly believe that quantum mechanics should not contradict relativity. So this assumption, again, is sort of like, if you like, a security patch. Quantum mechanics is threatening to be hacked, to hack relativity, if you like. So we download a patch that prevents it. So is it actually correct? So how do we know there are not cross terms in the Hamiltonian? And what would that mean? What it would mean is, so the Hamiltonian gives you the possible energy states, or energy eigenstates is the technical term, for this for a system. And what this would mean, if you had an H1, H2 term here, what it would mean is there are energy states of the combined system. The system as a whole has energy states that are not localized to the particles. That's what it would mean. And is this right? So I had a conversation with Abner Shimoni in 1993 and asked him, I said, why don't you have cross terms in your Hamiltonian? And he said to me in a very shocked voice, oh, but then we could violate parameter independence, which is no signaling. So he just put it in there so that his quantum mechanics wouldn't violate signaling. And then he turns around and proves no signaling from an assumption that is designed to prevent no signaling. So I have a lot of respect for Abner Shimoni. He was a very, very wise and smart person, but I think this was the wrong way to go about it. So what does the physics actually demand? So that's it's not just a question of whether or not the argument is circular, because you can debate endlessly about that. But the question is, what's the physics actually demand? Well, if you dip into more recent literature, for example, there's enormous amount of literature now on what's called quantum information theory, and I dipping into this one paper from which was in Physical Review, one of the Physical Review journals in 2002 by Jur et al. They give it an expression for the general Hamiltonian for an entangled state of two particles. Sometimes these are called Bell states as well. Now this may look rather complicated, but it's really just what I had on the previous slide with more bells and whistles on it. So this thing is Hamiltonian for one particle A, if you like. This is the Hamiltonian for particle B. And what this little thing says is that this identity here says this does not affect A, does not affect B, B does not affect A. But the third term here, you've got the cross terms between A and B. And you can't in general make this third term go away. So within quantum information theory, the idea of entangled Hamiltonians is just, it's all in a day's work. They just accept it. And I actually wrote to Professor Dürr and asked him, like, where did he get this from? And he wrote back to me, very politely, but he basically said, this is so elementary, we didn't even bother to prove it. Everybody knows, right? So here's a funny thing. You have the foundational literature assuming one thing, and you have ordinary workaday researchers in quantum information theory assuming something very different. So now here's a couple more things. There's a really interesting paper published in 2011 by Lee, Sprague, and some other people involving a very complicated interferometer. I don't fully understand how it works, but the gist of it is they have two little chips of diamond about 3 millimeters apart in size, 30 centimeters apart, completely physically unconnected. And they get zapped with a laser beam and put into the same energy state. And this is demonstrable. And they ran the experiment, I think, 200 trillion times. So they got pretty good statistics on this. And I've given you a couple of links here. And again, I'll show my references at the end of the presentations. If anybody wants to look this up, they can do so. So to see the details. But it's here you have an experiment done just 10 or 11 years ago, which demonstrates, I mean, directly demonstrates dynamic non-locality for entangled states. So nobody seems to have noticed this. I've seen no discussion of this in foundations of physics literature. Mind you, maybe I'm not up to the literature. Maybe I missed something, but people should be talking about this. So there's a kind of what I would call a cognitive dissonance going on here right now. It's very well known that entangled quantum systems are not always dynamically local. And, you know, I didn't even mention Bohm's quantum potential, which is also a form of energy. And I mean, I've seen papers where people say, oh, Bohm's quantum potential carries no energy. That's just a mistake. It is a form of energy. You can easily see that from the math. So, and it's in general non-local. But let's not get into Bohm. That's another that's another 4 or 5 interviews or talks, I think. So, but this just hasn't penetrated these foundational discussions. And what everybody wants to show is, yeah, Bell's theorem, we know all about that, but don't worry, relativity is okay. We can just go on, business as usual. Now, I'll just show you just quickly a little proof that I came up with myself to help demonstrate part of the problem with Shimoni's argument. And I'll kind of do this fairly quickly. It's a little bit technical, but not too much. And then we can pull back and look at the larger picture. So this is an example of a reductio or ad absurdum argument, or a proof by contradiction. So background to this, if you dig into Cohen-Tanucci or other good books on quantum mechanics, they'll tell you something like this: the subsystems of a tensor product state cannot be pure states. And so Cohen-Tanucci say, it can be shown that an interaction between the two systems transforms an initial state, which is a product, into one which is no longer a product. Any interaction between two systems, therefore, induces in general correlations between them. This is entanglement. This question is very important since, in general, every physical system has interacted with others in the past. Now, if you stretch your mind a little bit and go a bit crazy and think about cosmology, what is our dominant picture of cosmology right now? The Big Bang picture, where every particle in the universe interacted closely with every other particle in the universe in the past. So therefore, on this view, the entire universe is an EPR apparatus. I think that's a very cool thought, and not enough thought has been given to that point. But let me press on. Key point here, that again, quoting Cohen-Tanucci et al., they say it is not possible to associate a state vector, a pure state, with an individual system alone if it's part of an entangled state. Okay, but let's go on. Now we do the proof by contradiction. Suppose you could associate a Hamiltonian with a particle H1 with a particle P1 that's a member of an entangled state. Well, here's some. Now you have to dip back into Cohen-Tanucci again, and the other thing you'll find, this is sort of quantum mechanics 101. If a particle is associated with an observable, a Hamiltonian is a kind of observable. It just means a linear operator for a thing you can observe. Every observable associated with a state has a set of eigenstates which define what's called a basis for psi. So therefore, if this particle, quote unquote, has a Hamiltonian, it would be possible to write the state of that particle as an expansion of that form, where these C's are complex coefficients. So it's just a linear superposition or linear combination of the eigenstates for the presumed Hamiltonian. But the trouble is, any expression of this form is a pure state, right? So But that's impossible if the particle is entangled. It just has what are called mixed states. And so if you have an entangled system, the system as a whole is said to be pure, such as the singlet state. And then each individual particle, to the extent that it's individual at all, has what's called a mixed state, which is basically a classical probability distribution over pure states. So if you just look at the individual particle by itself, you can't know what pure state it's in just by local measurements as we understand it. So this is because P1 is taken to be a member of an entangled state, it cannot by itself be represented as a pure state. So either there cannot exist a Hamiltonian that can be assigned to each individual particle in an entangled state, or the state is not entangled. It's really just a product state. So if you want to get a little bit surety about this, you can say any no-signaling argument that depends upon the assumption of additivity is merely a trivial demonstration of no signaling for product states. And of course, there's no signaling with product states because they are, by definition, independent. And product states do have additive dynamics. That's well known. Okay, so to summarize all of this in a way that's not exactly precise, but it makes the point. There's no signaling because there's no signaling, damn it. Okay, that's basically what these no signaling theorems, despite all of the fancy algebra, that's what they amount to. And I mean, I strongly emphasize, I do not know whether it's possible to construct a controllable signaling device. I don't have a blueprint for one in my desk here. I mean, I just don't know. But what I do feel is that the usual arguments given against this just don't work. They just don't work at all. So if somebody wants to come up with a sound proof of no signaling in quantum theory from the basic principles of quantum mechanics, they can't just assume that it works. You've got to use some other method, and I'm not sure what that would be. So in my humble opinion, the question of controllable signaling is still an open question. Okay, so I'll stop there, and then I'll just briefly show my references here, and if somebody wants to pick that off the video, they should be able to do that. Okay, so that's my story.